The simulator maps fluid behavior around a curved obstacle by employing a complex conformal transformation that seamlessly converts a parabolic surface in physical Cartesian space into a straight, flat boundary line within computational space. Operating under ideal, potential flow assumptions, incompressible, inviscid, and irrotational fluid, the mathematical engine enforces a strict kinematic boundary condition, ensuring that normal fluid velocities drop identically to zero along the obstacle surface. Introducing an angle of attack dynamically alters this balance, shifting the zero-velocity central stagnation point downward along the windward flank and forcing the fluid to accelerate rapidly over the upper leeward flank. To translate these fluid velocity fields into visible physical forces and live graphics, the simulator relies on a fast, multi-threaded rendering and numerical pipeline. It evaluates local fluid speeds across a grid of spatial blocks, translating them into localized pressure metrics via Bernoulli's equation to generate real-time color-coded heat maps and drive an explicit Euler advection loop for dynamic tracer particles. Simultaneously, the diagnostic system executes a live numerical integration of the surface pressure differences between the opposing flanks, quantifying the net aerodynamic suction imbalance to compute and display the relative lifting forces experienced by the obstacle.